Okay, here we're going to take a look at Module 2, Force and Momentum. So if you didn't get this completed yet, you can now go in and complete Force and Momentum. Okay, and number 1, a boat moves through the water. There's 2 forces acting on it, or 2 that they're considering. One is the force that is pushing the boat with the propeller. That one's acting at 800 newtons. Then there's a resistive force due to the water that the boat encounters as it's going through the water. So that force is acting in this direction. So what we have to do is sum those forces, and since they're acting against each other, we subtract them. So we have a sum of forces at 600 newtons. Okay, it should be showing my calculator, and we'll take the 1800 minus the 1200 for a net force of 600, and then we divide that by the mass of the boat, 1500 kilograms, and we get 0.4 meters per second. Since there are 4 significant figures here, then we would need 4 significant figures in our answer. Okay, next we want to look at if it starts at rest, how far will the boat move in a certain amount of time, in this case 25 seconds. All right, so the distance moved, we look at down here, the change in the x direction, which is this way, is the initial velocity times the time. Well, it told us it started at rest, so if the initial velocity is 0, then this just goes to 0. Next, we have 1/2 AT squared for our distance. So we take our 0.4 times 0.5, or divide it by 2, and then multiply it times the time squared. All right, so I have my acceleration. I'm going to multiply that by the time. Actually, first I multiply it by 1/2, or divide by 2, whichever you prefer. And then I'm going to multiply it by my time, but I have to square my time, and then hit enter. Okay, so it went 125 meters. I do have 3 significant figures in my problem here, so I would limit my answer to 3 significant figures. The final velocity, what's the final velocity at the end of the time? So at the end of the 25 seconds, what's the final velocity? So we take the initial velocity plus the acceleration we calculated in A times the time given in B. So 0.4 times 25 is 10, and we do need 3 significant figures in our answers, so we write it as 10.0. Okay, here we're looking at a rocket taking off from Earth. So he's accelerating upwards at 61.2 meters per second squared, and gravity is acting downward at 9.8 meters per second squared. So we need to find the sum of those forces. Here's the equation. The sum of the forces is equal to the mass times the acceleration in the y direction. Okay. Okay, so those two forces are going to subtract from each other here, and we set that equal to the mass times acceleration. And then we move mass and gravity over to this side by adding it. And we're left with N equals mg plus ma, which is the mass times gravity plus the mass times acceleration. Or you can pull mass back out. Either way you do this, the math comes out the same. That's the whole point of that rule. So we add the two accelerations together, acceleration due to gravity and the acceleration due to the speed of the rocket, and multiply it times the gravity. I'm sorry, the mass. Okay, so our answer comes out like this. They want 4 significant figures, or 3 significant figures, so it would be 6030. You just move your decimal point 3 places to the right. 1, 2, 3. So that would make that 6,030. Okay, here a girl exerts a horizontal force of 133 newtons on a crate with a mass of 34.7 kilograms. If the crate doesn't move, what's the magnitude of the static friction in newtons? And that's the easy one to answer. It's going to be 133 newtons. The static friction being applied, if it's not moving, is what is the minimum possible value of the coefficient of static friction between the crate and the floor. Assume the crate remains stationary. Okay, so here we're looking at the static friction has to be less than or equal to the coefficient of static friction times the mass times the gravity. So then if we solve for the coefficient of static, we have the frictional force, or the static force that's applied divided by the mass times gravity, or acceleration due to gravity. So we have 133 newtons, which was the applied force, which is a static force, and we divide that by the mass of the crate that was given times acceleration due to gravity. All right, so let's put that in the calculator. 133 divided by 34.7 times 9.8, and we have 0.391, and we will leave that with, here's where they confuse me because these all have 3, this is 4. 3 significant figures, or 3 decimal places. 3 significant figures is what I would go with there. The 0.391. 0.391. Okay, and this one, Sally and Sam are in a spaceship that comes within 16 kilometers of the asteroid Ceres. Determine the force Sally experiences in newtons due to the presence of the asteroid. They give us the mass of the asteroid and the mass of Sally. And they give us G, which is the gravitational constant. So we'll use G here. All right, so F equals G times M1 times M2 divided by the distance squared. All right, so we have G, M1 is the mass of the asteroid. M2 is the mass of Sally. We multiply those three together and divide by the distance squared. The distance here is 16,000 kilometers. We convert that to meters, so it would be 16 million meters. And then they use scientific notation, so that would be 1.6 times 10 to the 7th. I would have actually done 16 times 10 to the 6th. I'm an engineer though, not a scientist. All right, so let's look at that one on the calculator, and we take 6.67 with an exponent of -11. And don't forget, you have to use the negative sign, not the subtract sign there. And then we multiply that by 8.7 with an exponent of 20 times 69 kilograms. And then I'm going to divide that by my distance, 1.6, with an exponent of 7. And I need that number squared before I hit equal. Okay, in that case, our least number of significant digits, I'm not sure why they're giving us 4 here, because there's 2 in this number here. Anyway, our answer, the answer they're looking for has 4 significant figures. Not sure the logic on that, sorry. All right, with number 5, you have to go through and watch each step of this and then come back and answer these questions. So, like most people think, this is not the intuitive answer. Most people think that the bigger car will have, since it's bigger, it has a greater force, but when the two collide, they become one system, and the forces are actually equal to each other. It's what you see after the collision, that's the distribution of the forces. So later in the video, later in the vignette, a video of the collision between the cart and the large mass and the one with the small mass is shown again. The forces during the collision are plotted. What does the plot of the forces indicate? That the forces that the cart exerts on each other during the collision have the same magnitude but opposite directions, meaning it's the same force, just in opposite directions. And consider the collision between the carts of unequal masses shown in the vignette. Which of the following statements is true about the forces exerted by the cars on each other during the collision? The forces are equal in magnitude and opposite in direction, according to Newton's third law. The collision between the lighter and the heavier carts is shown again with the small toy figure riding in each cart. Which of the following statements is true about the different effects on the toy figure during the collision? Well, the forces each cart exerts on the other has the same magnitude. However, the lighter cart has a lower mass and takes more of the acceleration away, and the heavier cart takes away less of the acceleration. The force each cart exerts on the other has the same magnitude. However, the lighter cart has a lower mass than the heavier cart, and therefore, according to Newton's second law, it has greater acceleration. And they show you that comparison when you put M1 and M2 and A1 and A2 on different sides of the equation. Okay, here we're looking at a spring. With the spring, I'm not sure why that won't go right now. It has a mass of 0.7 kilograms. It's attached to a spring with a force constant of 148 Newton meters. The cube rests upon a frictionless horizontal surface. Okay, the cube is pulled to the right a distance of 0.12 meters from its equilibrium position and held motionless. Sorry about that. The cube is pulled to the right. Oh, okay, that's where we were, and held motionless. The cube is then released from rest. At the instant of release, what's the magnitude of the spring force acting on the cube? Okay, so we look at Hooke's law. And Hooke's law dictates that the force exerted on the spring is opposite in the direction to its displacement from the equilibrium, or where it was at rest, proportional to the magnitude of that displacement with the constant of proportionality K. So that's the spring constant being a property of the spring. So they have the force in the x direction is equal to minus the spring constant times the displacement, or the distance that it moved. Where the subscript x reminds us that this force operates along the axis of displacement, meaning the x-axis or side to side. That is, the axis along with the spring is stretched or compressed. That doesn't, okay. Yeah, it's just saying along the axis that it moves on. The distance A is simply the absolute value of the displacement. Okay, so it's the absolute value of the 0.12 meters that it moved. And so the amount of force exerted by the spring upon the cube is K times A, K being the spring force constant and A being that distance. The magnitude of the cube's acceleration along the spring axis is given by Newton's second law. So we take the absolute value of the force divided by the mass, or 17.8 newtons that we just calculated, divided by the 0.7 kilograms for the mass that we were given. And our acceleration is 25.4 meters per second squared. Okay, and then C looks at in what direction does the acceleration vector point at the instant of release? It points toward the equilibrium position, which means once you pull a spring past its equilibrium and then you let it go, that's the direction it's headed back in, is toward the equilibrium, or where you pulled it from. Okay. Number 7, throwing a rock in a boat. The figure below shows the fisherman in a canoe on the lake. The fisherman's mass is 73 kilograms. The canoe is 119 kilograms. The fisherman and the canoe are initially at rest. When the fisherman throws the package I like rock better. Package sounds a little suspicious. No wonder he's wearing dark shades, but he shouldn't have on a yellow shirt anyway. Has a mass of 15 kilograms horizontally to the right with a speed of 4.6 meters per second. So that's the initial speed of the package. What is the velocity of the canoe after the package is thrown? Neglect any resistance force from the water. Give the magnitude in meters per second and select the correct direction from the options given. Okay, so let's look at the magnitude. The canoe and the fisherman move as a single unit having mass. So we add the two masses together. And the whole mass of the man in the canoe was 192 kilograms. Yep, those came from right here. Before the package is thrown, all parts of the system, canoe plus fisherman and package, are at rest, so the total initial momentum is 0. Neglecting water resistance, the final momentum of the system must also be 0. Or we look at the mass of the canoe fisherman times the velocity of the canoe fisherman plus the mass of the package times the velocity he threw it at. So yes, that's a complete sentence there. And all of that added together equals 0. All right, so if we want to solve for the velocity of the canoe fisherman, we multiply through by VCF, by MCF, move it to this side, so we have the mass of the package divided by the mass of the canoe fisherman times the velocity he threw the package at. And that will be minus, meaning it's in the opposite direction. Okay, so that gives us negative 0.359, and that would be toward the left. Okay, now last one. 2 football players collide head-on in midair while chasing a pass. Saw that the other night in a Falcons game. They weren't going after a pass there. First player has 101.5 kilogram mass and an initial velocity of 5.1 meters per second, while the second player has a 114 kilogram mass and an initial velocity of negative 4.1 meters per second. That just means it's in the opposite direction. What is their velocity just after the impact if they cling together? Indicate the direction with the sign of your answer. Indicate the direction with the sign of your answer. Okay, since there's no horizontal forces involved in the collision, momentum is conserved. So the first person is traveling in the X direction, and since we have a head-on collision, the second person is traveling in the negative X direction. A statement of conservation of momentum may be written as the mass of the first person times the velocity of the first person plus the mass of the second person plus the velocity of the second person is equal to the two masses added together times the velocity prime, where M1 and M2 represent the mass of player 1 and player 2, and V1 and V2I represent the initial velocity of the two players. And V represents the velocity of the combined, that should have a prime on it. V prime represents the velocity of the combined mass of the two players. So if we solve for V prime, we just have that M1V1 plus M2V2 divided by M1 plus M2. Okay, so we can look at that one on the calculator. Okay, so M1, 101.5 times 5.1. I'm going to get an answer to that. And then I'm going to add to that and use my parentheses. 114 times 4.1 negative, and get an answer to that, and then divide that by, and since this is added, 101.5 plus 114, close my parentheses, and we have 0.233, and we'll leave it at 3 significant figures, although there was only 2. Still trying to figure out what they do sometimes. Right, those were added, so that's significant digits, not figures. And then when you divide, it's significant digits, or significant figures, not digits. Okay, hope you enjoyed that. Let me know if you have any questions. Thank you. See you later.